In Level 3, we will be solving more exponential and logarithmic equations, but we will also have to apply our properties of logs, meaning our product rule and our quotient rule. So in this first example, I'm going to start by combining these two logs into one expression using the product rule. Since the logs are added together, I can multiply the insides. So I get log of 3x minus 2 times x minus 1 equals, and then using the power rule, I'm going to move that 2 up to be an exponent, and I get log of x squared. Now, one method you can use, if you have two logs with the same base set equal to each other, for this equation to be true, the inside parts would need to equal each other. So I can just make that into a new equation, 3x minus 2 times x minus 1 equals x squared. And I solve that equation. So to solve this, I'm going to multiply this out. We get 3x squared minus 3x minus 2x plus 2 equals x squared. I'm going to subtract x squared from both sides. Since this is a quadratic equation, I want to solve by factoring if I can. So we get 2x squared, combine like terms, minus 5x plus 2 equals 0. And then hopefully this will factor. We put 2x and x, and I probably want a 2 here and a 1 here. And if these are both minuses, I get minus x and minus 4x, which adds to minus 5x. So I was able to factor that. And we set this equal to 0 and figure out what makes each part 0. So 2x minus 1 equals 0. Add 1 to both sides, 2x equals 1. X equals 1/2. And then on the other side, x equals 2 would be the solution that makes x minus 2 0. Now, whenever you solve log equations, you need to make sure that neither of your answers makes the inside of a log negative. We can't take the log of a negative number, it's undefined, because if you remember, the graph of log of x looks like this. It doesn't have any negative x values in its domain. So I can't take the log of negative 5, it's undefined. The graph doesn't even exist when x equals negative 5. So I always want to check my answers and make sure they don't make any of the inside of the log negative. If I plug in 1/2 right here, I get 1/2 minus 1, which is negative 1/2, and I can't take the log of negative 1/2, so that's undefined, which means this is an extraneous solution. Plugging in 2 to all these logs is going to be okay. So my answer is just x equals 2. So always remember to check your solutions when you're solving log equations. Make sure they don't make the inside of any of the logs negative. In this next example, we are going to combine the two logs into a single expression first. So using my quotient rule, since we have subtraction, we're going to divide the insides of the logs. So to smush it into one log, I do natural log of x plus 1 divided by x plus 4 equals 1. And now that I have it condensed into a single log, this time I'm going to change this to exponential form. So this is the same as log base e of x plus 1 over x plus 4 equals 1. And to change this to exponential form, I get e to the first power equals x plus 1 over x plus 4. And this is the equation I have to solve. So to solve for x, since x is in two places, first I'm going to multiply both sides of the equation by x plus 4. Okay, and those cancel, and we get ex plus 4e equals x plus 1. And then I still have x in two places. I want to get my x terms to the same side, and everything that doesn't have x on the other side. So I want this x to go to that side, and I want this 4e to go over here. So subtracting x from both sides, we get ex minus x equals, and then I'm going to subtract 4e from both sides, and I get 1 minus 4e on the right side. And now I can factor x out on the left side, and I'll get e minus 1 equals 1 minus 4e, and then I can divide both sides by e minus 1 to get x by itself. The e minus 1's cancel here, and we get x equals 1 minus 4e over e minus 1. That's a goofy looking answer, but remember that e is just a number, so I could plug this into my calculator and get a decimal approximation if I wanted. This next example is a real-life application of an exponential equation that we're going to solve. It says $10,000 is deposited into an account with 5% annual interest compounded continuously. How long will it take for the account to be worth $15,000? Use the formula A equals PE to the RT, where P is the initial amount invested, A is the amount of money in the account after T years, and R is the interest rate. Solve algebraically and use a calculator to approximate your answer to the nearest hundredth of a year. So we're using this formula A equals PE to the RT. P is the initial amount invested. And in this account, it says that $10,000 is deposited. So that would be our P. So P is going to be 10,000. E is just a number. The interest rate is 5%, but remember to always change that to decimal form, so that's going to be 0.05. And the question is asking how long. T is what we're going to be solving for. And we want to know how long it will take for the account to be worth $15,000. So we want the amount in the account to be $15,000, which is our A. So we put 15,000 on this side. And now we are solving this equation. So I want to get the exponential part by itself first and then I'm going to end up changing it to log form. So my first step is going to be to divide both sides by 10,000. And we get 1.5 equals e to the 0.05 t. And now that I have the exponential part isolated, it's all by itself, I'm going to solve this by changing it to log form. Changing this to log form, we would get log base e of 1.5 equals 0.05 t. Now remember, this is natural log of 1.5 equals 0.05 t. And then to solve for t, all I have to do is divide both sides by 0.05. And we have t by itself. T is equal to the natural log of 1.5 divided by 0.05. And then to get a decimal approximation that makes a little more sense, we're going to plug this into our calculator. Now, when you plug it in, make sure you do the natural log button. Then it gives you a parenthesis of 1.5. Close that parenthesis, then divide by 0.05. And you get approximately 8.1 11, I guess, if we round to the nearest hundredth. So that's about 8.11 years is our final answer.